numbers 48 and 72 as prime factors. Oh, you can't see that. Sorry. So, prime factors of 48 and 72. Do you have a preference? Which method do you like? Tree, division, somebody like division. I know somebody like tree. So it really doesn't matter. I'm not going to ask you one method or the other. You just choose whatever you like and do that. Okay? So why don't you try these two? We are at the 8 already? We just did that one, right? On the board? Was that part of your example? It was, right? It was 2 to the power 4 times 3, right? I think. Am I wrong? Easy way to check that. On these calculators, just the hat button is the power. So the hat is this one right here. And then 4 times 3. Yeah, okay, so that one's good. So let's do 72, because we haven't done 72. So you can either do tree or division. So I'll write both, you choose which way. 'It's even, so 2 can go into it. How many times? 36. 2 goes into that. How many times? 18. And 2 can go into that one. 9 times. And last, 3. So 72 would be 2 to the power of 3 times 3 squared. So in junior high, you did cover greatest common factor. It usually wasn't with multiple, like it was maybe smaller numbers that you did it with. So you did a couple and they're a lot smaller. So it was easy to find because we just list all the factors, make a multiplication table, and then we can find the greatest common factor. So for example, in grade, I don't know what grade it was, I think it was 9, maybe 8. Like for each one of these, we could just make a chart, right, of all of the a multiplication chart. 8, what are the ways we can multiply to 8? 2 times 4 and 1 times 8. 16, all the ways to multiply to 16. 2 times 8, 4 times 4, and then 20. 2 times 10, 20 times 1. Okay, so when you're done. Looking at this, what's the greatest common factor? What is the greatest number that they have in common for their factors? 4, right? That's what you would have done in the past. You just make a multiplication table, and it's 4. So why don't you try C on example 1? I'd like you to make a multiplication table for 36 and 54. And start with that and see if you can find the greatest common factor. Grab your calculators if you have to, right? Start dividing. Okay, 1 times 54, 2 times? 2 times 20, there we go. 3, 18, 4, does 4 go in? Nope. 5, nope, just 6. 6 times 9, are there any other numbers? So you just have to check 7 and 8, and they don't go into 54. So looking at that, what is the greatest common factor? So the greatest common factor, again, is the largest whole number which divides exactly into both numbers. 18. 18. Okay. Oh, that is not a pen. There. 18. So that would be your GCF. Now, that's fine if our numbers are small. It also is fine if we're only doing a couple numbers. But once we start to do 3 or 4 sets of numbers, it starts to be a lot more tedious, and especially if the numbers are larger. So we actually can use prime factorization to find lowest common multiple and greatest common factor. And so when we look at the prime factors, so we had, remember these sets of prime factors from above? 72 was, oh no, that's not right. That's the GCF. Erase this. 72 was 2 times 2 times 2 times 3 times 3. So we look at the prime factors and we want to see what they have in common. Okay, comparing the two lists, what's the same when we look at the prime factorization? So they each have at least 1 2 in common. They have another 2 in common. What else do they have? Do you have 3 2's in common? Yeah. And what else do they have in common? 1 3. So that would be our GCF. Our GCF is what they have in common. So it would be 2 times 2 times 2 times 3. And so now we can just figure that out. Grab your calculators. 2 times 2 times 2 times 3 is 24. That is not a pen. Again, 24. Okay? For these two numbers above, 48 and 72. That would be the greatest common factor. So we're going to try a couple with prime factorization. It doesn't matter the method you use. Okay. So let's prime factorize both of these, and then we're going to list it a product of prime numbers. Okay. So if you use the division table, you only can divide by prime numbers. If you're using the tree, you just need any two numbers that multiply to 90. Okay, so you could use 9 times 10, for example, if you're using the tree. Division, I'd probably start with 2. Yep. Check your answer. Okay, so 225 is a little bit larger. So 2 won't go in, and divided by 3 is 75. 3 will go in it again because the digits add to 12. And so if you add the digits together, it's a multiple of 3. And 3 will go in it, so 25. And then 5 and 5. So you should have 3 times 3 times 5 times 5. So let's find the GCF. What would the GCF be? What's in common in both sets? They both have two 3's and 1 5, right? That's what they have in common. So the GCF would be 3 times 3 times 5. That's what they have in common. Which is, you said 75? 45. That makes sense. That would be your GCF. Okay, let's try the next one. I tend to use the division table. It doesn't matter though what you use. 76? 77, yes. No, that's good. And then what else goes into that? What's the next prime that goes into 77? 7 and 11. 99. 3. We only want to divide by primes, right? And that gives me 33. We can divide that by 3, which gives you 11. So even looking at your tree or looking at this, you might be able to see what's in common. So what do they have the same? 2 and 11. So the GCF would be 11 times 2, or 22. Okay. So we're going to do one of the examples of number 3 on the next page. You choose which one you want to do. A or B? First one who says it wins. A, what? A, okay, let's do A. There are only 3 numbers instead of 4. So we're going to find the greatest common factor of these sets of numbers. So notice that they're larger. They're a little bit tougher. If you tried to make a division or a multiplication table, they're larger. Okay. So we're going to find the greatest common factor. The greatest common factors are always smaller than your sets of numbers, right? They're the factors. Keyword is factor. So make your trees or division table. Let's prime factorize each one. So what will go into 245? Let's do this together. 5 times 49. 49 should be simple. Divided by 7 is 7. So 245 is 5 times 7 times 7. 315. Divide by 5. 63. Divide by 3. 21. And what else can we divide that by? 7, and it gives you 3. So when we list them, like it doesn't matter the order. You might have had a different order. Maybe you divided it by 3 first instead of 5. But we just list them from lowest to highest numbers. So we have 2 3s, 1 5, and 1 7. And it doesn't really have to, but it's a proper way. And it's easier when you're comparing what's in common. Okay, 770. Divide by 10. Nope, 10's not prime. We can do 2. 53, 60, no, 385. 2 won't go into that. 5, sure. And that gives you 77. Well, that's nice. We can divide that by 7. It gives us 11. So, don't forget to include the prime number on the bottom too, right? So we have 2 times 5 times 7 times 11. So what do they have in common? A 7 and a 5. So what would be the GCF? What's in both or all 3? 5 times 7 or 35 would be your GCF. Okay, that's good? Not so bad? We're good to go on? Yeah, okay. So where students get hung up is lowest common multiple. Like just confusing the two. So you have to make sure you remember like factors, right, is always, notice our answer is always smaller. Oh, it got moved. We had 2, 4, like the factors. It has to be a factor of all 3 of these. It has to divide into all 3. It's a factor. Multiples, right, when you have a multiple of 3, give me a multiple of 3. Any multiple of 3. 6, 12, 9, right? It's larger. So even though when we say don't get the lowest, you want the lowest common multiple. The lowest number in common that are multiples of all our numbers. So again, we can use prime factorization. Now, back in junior high, you would take your 2 numbers, they were nice and small, and you would write out its multiples. So 6, I go 6, then next is 12, 18, 24, 36, right? At 8, I would do the same thing. 42, 8, 2. Okay, so 8 would be 8, 16, 24. Can I stop? Yes. 32. So, oh, I missed 30. Sorry, guys. I just skipped 30 altogether and added 12. So the lowest common multiple would be 24. It's the first multiple in common. And that's totally fine if our numbers are small and it won't take us 5 hours, right? But if we're dealing with multiple numbers and large numbers, that could take you all day. I've seen it. I've seen students on a test try and write out all the multiples, and they fill up like half of a page of paper in small writing in one number, and then the next number, and the next. You know how long that takes? You're not going to finish your test if you do that, especially if they're large numbers. So, when we're finding lowest common multiple, we can again use prime factorization. I don't know if you notice a theme here. Always prime factorizing. But we write each of them as a product of primes. So let's do this example of, here they did, 10, 12, and 14. Okay? So we wrote out the prime factors. We write out the string of the product of primes. 2 times 5. 12 is 2 times 2 times 3, and 2 times 7. Okay, so what you want to do is start with your longest string of product of prime numbers. So the longest one was 2 times 2 times 3. Okay? Every single prime number has to be represented. So what I mean by that is that I start with 12, and I have 2 times 2 times, well, let's just write that. 2 times 2 times 3. So start with your first one, because all 3 things right there. Okay? Now I check with, let's look with 10. Is the 2 already in there? Got 2. Yeah, that's included. Was the 5? No, we only had 2 and 2 and 3, so we're going to add the 5 in. Now it's included. Now I go down to 14. Was 2 there? Yeah? Is 7? No, so I need to include it. And so that's how I get my lowest common multiple. All of these have to be included in this, okay, to get the lowest common multiple. And so now we can multiply these together. 2 times 2 times 3 times 5 times 7. What does that equal? 10. Let's do it together. 2 times 2 times, is 420. Did you get the same thing? That would have been like, if we had to list all the multiples of 10, 12, and 14, that would take a while to get to 420, right? So this is going to be a lot quicker method to finding lowest common multiple. So let's move on to the next page. Okay, and let's skip A and go straight to B. Those numbers are lame. Let's try B. So prime factorize, if you want to use a tree, you can use a tree, or if you want a division, I'll do division. Remember, only divide by prime numbers. So first prime number would be 2, which is 63. 2 won't go in, but what will? 3, 21. And then last, 3 and 7. 441. 2 won't go in, but will 3? Yes, because 4 plus 1 is 9. You add the digits together. That's a multiple of 3. Then 3 will go into it. So 3 will. And what does it, how many times does it go in? 147. Okay, 7 plus 1 plus 4 is 12. So guess what will go in? 3. How many times? 49. And now it's easy. 7 and 7. Now, both strings are the same, right? They're both 4 numbers. And this one's 3 times 3 times 7 times 7. So it doesn't matter which one we start with to find our lowest common multiple. Which one do you want to do? The first one or second? Sure, let's write the first. Doesn't matter. Pick one. Okay, we're going to write it out. The whole string. Okay, so now we know all of those are included. We're good. So let's check. Go through one at a time. The first 3, is it there? Yes. Second 3, is it there? So we need 2 3s? Yeah, both there. Good. So we had a 3 and we had a second 3. Good. 1 7, is it there? Is the second 7? No, so we have to include it. It was missing. Right, so if there's 2 7s here, our LCM needs 2 7s. Okay. So multiplying that all together, what does that equal? 820? 82. Thank you. So now both 7s are there. Let's try this guy. 22. 2 and goes in. How many times? 11. That one's easy. Done. 154. 2 times 77. And we can divide that by 7. I feel like we just did 198. 299. And then 3 was 33. 3 was 11. Let's write them all out. 2 times 11. This was 2 times 7 times 11. Last one was 2 times 3 times 3 times 11. Okay, so we're going to find the lowest common multiple. Where would I start? Pick the longest string and write it out. The longest string is 198. 2 times 3 times 3 times 11. So now we've included those. Those are good. So let's start at 22. Is 2 and 11 there? Yes, we're good. 154. Is 2 there? So 2's there already. So we're good. It's represented. Is a 7 there? No. So now it is. We're good. And is 11? Yes. So our LCM would be 198 times 7. 600. Oh, 1,386. 1,386. Do you see how that would take a while? You tried to write it all out? Yeah, you don't have all day for that. Okay, does that make sense what we're doing here? Like if I did, do you want me to do it in one more? Give it, do you want to Okay, perfect squares. You should know what a perfect square is, right? These numbers, 1, 4, 9. The ones that you can square root, and it'll give you a nice, beautiful whole number. Okay, those are your perfect squares. Every perfect square has 2 square roots, one positive and one negative. So what I mean by that is if I had x squared equals 49. Okay, there's 2 answers. There's 2 numbers that when you square them will give you positive 49. So if I square root 49, so if I have to square root both sides, it's going to give me plus or minus. When you square it, you have plus or minus 7. Because 7 squared would give you 49, but so would negative 7. Why? Yeah. A negative times a negative is a positive, right? And so when you square root both sides, you have 2 square roots, one positive, one negative. The positive is called the principal square root. We are only going to focus on the principal square root in Math 10. In Math 20, you're going to do both. Focus on both, okay? So in this lesson, we're working with only whole numbers, positive, whole numbers are only positive, right? Starting at 0. So we don't have to worry about the negative. We're going to only focus on the principal. So you can use prime factorization to figure out your perfect square. So 9 is 3 times 3. And so you can break it up into 2 equal groups. So then square root of 9 is 3, just one of the equal groups. Okay, so we split it up into 2 equal groups. 36 is 4 times what? 9, and then 4 is 2 times 2, 9 is 3 times 3. So if 36 is 2 times 2 times 3 times 3, we can split that into 2 same groups, right? 2 times 3 and a 2 times 3. Everything can be split in half. So half of them go here, half the 2's go here, half the 2's here, half the 3's, half the 3's. And so then the perfect, or square root of 36 would be 6. 2 times 3, one of them. 49 is 7 times 7, so 2 equal groups. Square root is 7, just one of them. And then 84, reduce prime factorization. Just give me 2 numbers and multiply to 64. 8 times 8. Did I say 64 or 84? I thought, yeah, sorry. I heard myself after, and I was like, that's not right. Anyways. 8, you can break into 4 times 2, 4 times 2. And we can still break up 4 into 2 times 2. So all our prime numbers, 64. You can we split into 2 equal groups? If there's 6 2's, how many would be in the first group? 3 of them, and then 3 of them. And so the square root of 64 would be 2 times 2 times 2, one of the groups, which equals 8. 2 cubed is 8. It's kind of a weird method, because you're probably like, well, I can just use my calculator. Yeah, you're right. You can. And with perfect squares, the biggest focus on prime factorization in this unit will be for GCF and LCM. Perfect squares might show up a little bit, but not too much. But it's just another way we can apply prime factorization, especially if we have like really large numbers. Like this guy. So first of all, let's use our calculator. If you are new to the TI, is it recording? Yeah. Square root button, you need to find. It's second x squared. So second, and then the x squared's right, oh, this is blurry. Right there, right above log. So second x squared, 44,100. Okay, so we're expecting to get 210. So let's have some fun. Square root of this, sorry. It's 210. Let's just play. So let's use prime factorization to prove that 210 is right. This is a nice large number. Now you're welcome to use the tree. Do you want me to use the tree? I always use the chart. I feel like I'm kind of biased. I'll use the tree this time. Especially because this one, what's a large number I can divide it by? 100. 2 zeros. That's nice. Now it's like not so bad. 100. 25 times 4 quarters. We'll worry about 441 later. 2 times 2 for 4, and 25. 5 times 5. Okay, 441. Well, they add to 9, so we know 3 goes in it. I don't know if you have a larger number that will go in. 9. 9 times 49. And then 9 can be broken into 3 times 3. And then 7 times 7. Okay, so the question is, can we split this into 2 equal groups? Yeah, because we have 2 2s, so one will go here, the other will go there. The 5s, can we split them up into 2 groups? Yeah, there's an even number of 5s. There's an even number of 3s. There's an even number of 7. So it is a perfect square. Where's my eraser? That's not an eraser. There we go. So the square root of 44,100 is equal to 2 times 5 times 3 times 7. Or, guess what that equals? Surprise, surprise. 210. Okay, I'd like you to try A. Yes, it is. Okay, we can split it into 2 equal groups. As long there has to be an even number of each prime. So there's 2 5s. Good. There's 2 7s. So what would be the perfect square? Square root of that is 35, just one of them. Right? Because if this is the same thing, we could also write that as 5 times 7 squared. Right? And so if we want the square root of that number, square roots and squares cancel each other. They're opposite operations. And that's why we're just left with 35. Okay? On a side note, I'll just write down, this one would have prime factorized to 2 times 3 times 3 times 13 times 13. Would this be a perfect square? No, not a perfect square. Why? There's only one 2. There has to be an even number of each prime that's represented so that you can split it in half. Okay, so not a perfect square. So perfect cubes are not a huge stretch. We just need to put it into 3 equal groups. So we need a multiple of 3 of each number represented. Okay, recording. All right, so 27, let's skip 27. Too easy. 216. 2 numbers that multiply to 216. Any 2. Somebody yell no. 8 and 27. Love it. So 8 4 times 2, and 4 we can break into 2 times 2. 27, the 2 numbers. Gotta know your times tables, hey? 3 times 9, and 9 is 3 times 3. So is this a perfect cube? Well, can we break it into 3 equal groups? So, yeah, you have to have 3 of each. So are there 3 2's? I don't know why I circled 9. It's not prime. Seriously, Johnson. Okay, yes, there's 3 2's. So 1 would go here, 1 would go here, 1 would go here. Are there 3 3's? Yeah. So what would be the cubic root of 216 then? Would just be one of the groups, which is 6. 2 times 3, or 6. Cubic root of 216 is 6.
What happens if you were to have 6 2's? Would you put 2 to the power 2 times 3?
Yes. So if you had 6 2's, so you have to have a multiple of 3 number of each prime. So then if you had 6 2's, you'd have 2 2's here and 1 3. Because you have to split them up, the 3 groups. So 2 to the power 2 times 3.
So yeah. If you were to have 4 2's, then you'd still have enough to make each group?
No, so if you had 4 2's, then it's not a multiple of 3, so it's not a perfect cube.
So you need to have all of your prime factors.
All your prime factors have to be represented, and they have to be, each one of these groups have to be the same. They'll split between all 3. Okay, so if there's 4 2's, not a perfect cube. Because 1 doesn't have home. Or you need 2 more for it to work. What's the next page? We'll do one more. Let's look at the last question. Number 8. It says, in each case, use prime factorization to determine whether the number is a perfect cube. Okay, we're going to do B. Because that one looks like fun. I obviously don't get out much. This is my idea of fun. So let's prime factorize this guy. Good thing there's some room here. So we're going to need it. Stick it together. I'm going to use the division table. I'm sorry for those who like the tree. 2 doesn't go in, does 3? Yes. Yay. Right, small. Okay, so you can just check by dividing. 2 6. I'll do it with you. So divide by 3. Good. 433. Does 3 go in again? So divide by 3. Yes. I'm not adding my digits together because I'm lazy. I'm just going to guess and check. Okay, I'm going to check one more time. Does 3 go in again? Yay! 3, 5, 9, 3, 7. Does 3 go in again? Yay! 3's popular today. 7, 9. I bet you 3 goes again. Sure does. And again. Yep. Okay, I know this one won't. Because the digits add to 8. So if you want to check, you can. Oops. Nope. So, okay, now we need something else. I know it is, but I want you to figure it out. 7 work? Nope. 5 won't. What's the next prime I could try? 2 won't, 3 won't, 5 won't, 7 won't. What's the next prime? 11. It does. Guess what goes into 121? 11. Not 3, because 1 plus 2 plus 1 is 4. But 11 does. Oh no! Where'd you go? What's left over? 11. So, can we make 3 equal groups? Yes, because so one group, whoops, there's 6, so there's 6 3s, so we can put 2 3's in the first, 2 in the second, and 2 in the third. And then the 11s, there's 3 of them, so 11, 11, 11. We can figure that out in our head. What is the cubic root of 970,299? 66, right? Oh no, 99. 3 times 3 is 9 times 11, 99. That was fun. Okay, so assignment. Some little bit more time today, but we have some extra, kind of ahead of schedule, which is good because when it gets, we need more time in class for some homework, we can take it. But the assignment is numbers. You might want to circle 1 to 7 AC. So if it doesn't have an A and a C, just do the A. Okay. And then, so 1 to 7 AC. Then 8, 9, 10 A and C. And then if time, you can try 12 to 14. But minimum, do those. Okay. And honestly, if you have time, do, like, before you try 12 and 14, do all of 4 and 7. Because those are good test type questions. So do this minimum. Again, if you have time, go back and finish number 4 and 7 because those are really good questions. And those are the type of questions that you want more practice of. Okay? Sounds good? Ready to start?